Start. Okay, so welcome everyone to the last algebraic geometry seminar of this semester. So today we're very happy to have Eroche Altabari Alberdi from the Mondragon University, and she's going to talk to us about K-stability in final varieties. So yeah, we start.
Thank you very much. Thank you for inviting me. Flora told me that you already saw a little bit of K-stability in some mini course and stuff, so that will be very helpful for me. I will start sharing screen, and I hope you all can see it. I think. Yeah.
Yeah, we can see it.
Can you see my screen? Yes, perfect. So yeah, today's talk is going to be a little bit of some results from my thesis and some of the results from other papers in collaboration with Avan, Chalchov, Denisova, Kalourikos, Yao, Martinez Garcia, Papazacario, and Jones. This is going to be, I will start, this talk will have 3 parts. So I will start first giving a little bit of an introduction to final varieties, very short, just to remember. Then I will, again, my dyslexia, a 2 becomes a 3 in my head. We will introduce very briefly K-stability, its characterizations and K-moduli and those things. Then we will focus a little bit on the local delta invariant, which also called local stability threshold. Which is one of the invariants that it's used to check to characterize K-stability, and we will finish with the talking about the Calabi problem for final threefolds. Okay, so this is more or less the idea, and recall that this talk will all be over C. Okay, so let's start. So let me just briefly give the definition of final variety. So we have the definition, which is X is Fano if it is normal projective variety whose anti-canonical divisor minus kx is ample. And now we'll focus in some examples, but let me, I cannot really see, oh yes, okay. Can you see this color well in the screen? Or do you rather have this one?
Maybe the orange is better.
Orange is better. Okay, yeah, my students also complain if I use the blue one. I understood, but so examples. And we will focus in the smooth ones during this talk. But know that there's already people working on singular final varieties. So the typical examples in dimension 1, and the only one in the smooth case is P1. In dimension 2, we have 10 smooth deformation families, which are Del-Pezzo surfaces. And we will talk about this later a little bit more in deep when we are talking about the local delta invariants. So here we have P2. which is 1 of degree minus kp2 squared is 9. Okay, then we have P1 cross P1, which degree its anticanonical divisor self-intersection is 8. And then the rest are the blow up of P2 in up to 8 points. Okay. The one that we will use later is one of this, the degree 1. We say no blue. So later we will see the case of degree 1, degree 2. Okay. So it's the blow up of P2 in 7 points. Okay. Remember that the degree is 9 minus the number of points that we are blowing up in P2 in general position. If that doesn't happen, we start having singularities. Okay, so, and in degree 3, we will also have a special example that we will carry through the talk. But in dimension 3, we have 105 deformation families. And they were classified by Koskik, Mori, and Mukai. Okay, and inside of this huge number of different deformation families, we will focus on family 3.12, which I will explain now what this means, which are the smooth members of this family are the blow up of P3 along the disjoint union of a line L and a twisted cubic. In P3. Okay. So basically we'll use this to see some K moduli later on. Okay, so I wanted to introduce them here. So we have a line and a twisted cubic inside of P3. And we blow them up and we get, this way we get all the smooth members. And the anticanonical in this case is 28. Okay. Okay, so once we have our main characters, let's say, of this talk, let's start with K stability. As I said before, technically, they told me you already know a little bit more about this topic, but anyways, if you have any questions, just interrupt me anytime. I'm happy to give extra explanations if needed. So in the second point, we introduce K stability and also a little bit of K moduli. So the initial motivation of K stability was really coming from differential geometry because they wanted to study Kähler-Einstein metrics and when variety will admit or not Kähler-Einstein metrics. And then, so this was Yao Tian, and Donaldson conjecture came across, where it says that a Fano variety X has a Kählerian metric if and only if X is K polystable. Okay, and this conjecture is now theorem. And this theorem was proven by a lot of people. I don't want to list everybody, but like for smooth cases, it was by Chen, Donaldson. Let me move this. Donaldson, Sun, and Tian. And then for KLT singularities, Li, Wang, Berman, Spotty, Sun, yeah. Okay. So yeah, a lot of people working on this, and they managed to prove this from both the smooth and KLT. And then after this was, I don't want to enter in the specific definition from K-stability or polystability because it's a little bit tricky. But what we really do usually to prove this K-stability, we have an easier definition that we'll see easier characterization for K stability, and this will imply K polystability. And there is a weaker one, which is K semi-stability. So in general, when we do computations, we don't check usually K polystability, but we focus on proving this, and then stability will imply polystability, or we will check that it is not K semi-stable, and then that will imply that it cannot be polystable. That's the usual approach, because checking this directly, unless we do have special circumstances, is a little bit complicated. So after soon we will start on this. But just to continue a little bit introducing why is K stability interesting for algebraic geometry, it's because why is it interesting for us? And this is because K stability allows us construction of moduli for Fano varieties. And so why is this so important? So for example, if we go back to the example we have here, and we have a family 312, which is like a family of blowing up a line adjusted cubic in P3. When we try to parameterize this, we try to get some moduli for this. It's supposed to be the parameterization for this is P1. So we have like for every element of P1, we have almost for all of them, we have like something like this. We can get a parameterization, but we have some issues. There is some cases where we have different deformations, singular deformations to this, and we have different examples. So we could have a line and a cubic and another line. We could have in the same point as the same limit, could have a line and 3 lines crossing, or we could have a line and 3 lines going through the same point. And this is an issue because the same point has 3 different possible elements. So we cannot really get a good moduli space, which is a variety. So then the good thing of K stability or K polystability is that only one of these 3 will actually be K polystable. So that will help us. That's how K stability allows this construction of moduli. After we will go in this example, we will go in details and we'll give the parameterization and we'll see how how we choose which one of this is good. Okay, but it's more or less to have an idea. And this is not the only good thing. So the uniqueness. So there is a unique K polystable limits, and this is a theorem that is proven, but this is not the only good property. We also have boundedness, the ness of the moduli. So when we have a dimension, a volume of K semi-stable objects, this is bounded. We have also Zariski openness. Also, we have that if X is K polystable, then the automorphism group of X is reductive. We have other properties as separateness, properness, and projectivity. So all good things that we are interested on. So now we mentioned a lot of concepts while we are interested on this. And now it's time to start with how we prove or how we check that something is K polystable. So for that, let me give you the definition. Few definitions we need to define K stability. So let F be from Y to X be a birational morphism. And we take E, a prime divisor on Y, or over X if you prefer. Then we define the log discrepancy as AXE to be 1 plus the order of E KY minus the pullback of KX. Then we also need to define the expected vanishing order. Which some people also call S invariant. Which is the integram from 0 to tau of the volume of the pullback of Kx minus T times the exceptional and volume X. Okay, in some literature, you might have seen some places you can see this to be infinity. Okay, but in reality, this tau is the pseudo-effective threshold, which is the supremum of T in Q, such that the volume of the pullback of Kx minus Te is bigger than 0. So even though in some literature you can see an infinity there is a point where this integral stops. So it's like after that point, this volume will be 0. So it's really a bounded integral. Okay, so even though in some places it appears like an infinity. Is there anybody in the audience that does not know what this volume is? Or should I just in case recall the definition of volume?
Yeah, we probably don't need it. Yeah, should be fine.
Should
be fine, yes.
Perfect. So once we have this, we can define the V invariant, V time variance for each E to be the difference between the log discrepancy and this expected vanishing order, XE. And we also have delta invariant, which is the X, the infimum of all the E over X of AXE over S minus X E. Okay, or which is the same, is the infimum of all the E over X, where we have a point. Sorry. Okay, we have delta invariant and we have, the local delta invariant of X. And this is local version. So the local delta invariant takes all the exceptional divisors over X such that P is in their center. And we compute this S minus Kx E. And we could compute the delta invariant as the infimum of all these local delta invariants. You might have seen before, this local version can be with any close subvariety. So I usually take it as points, but you could take any close subvariety and it still works. Okay. Good. So now that we have all these invariants, we use them to characterize K stability. So the theorem says that if we have X a Fano variety with at most KLT singularities, and E is a prime where E are prime divisors over X, then if for every E, beta E is bigger or equal than 0, this means if and only if X is K semi-stable. So we will have strictly bigger than 0, then we have K stability. If we have equality for some cases, then we have K semi-stability. And this is also equivalent to having that the delta invariant is bigger or equal than 1. Okay, so here we have to consider every E. Inside of the delta invariant, we are already considering every prime divisor over X, so we don't need to add that part. Okay, and we have an even stronger result, which sometimes can be helpful. Why? Because we don't want to check all these exceptional divisors. If we have to check absolutely everything, we can take forever, obviously. So it's helpful when we check that this does not happen, so that we have some exceptional divisor where this beta invariant is lower than 0, then all is good. But if we don't find any of that, and we think that it's k-poly stable, then we need some of the tools that will help us computing these things, improving this. And one of those is if we take G, a reductive subgroup of the automorphism group of X, for example, we have this theorem by Zhuang, 21, which says that suppose that beta of E is bigger than 0 for every G invariant prime divisor E over X, then X is k-poly stable. And this is very helpful. You have to think, for example, this gives, in the case of Pn, we have, this is known that it's not k-poly stable, k is stable. And actually proving that it's k-poly stable was a big paper, Anna's paper. But with this theorem, we can do it in a line. Because what is the automorphism group of Pn is PL n plus 1, which is reductive, so we can take it as G. And then there is no G invariant subsets of Pn. So directly Pn is k-poly stable. So it's a very powerful tool if you have a big automorphism group. If your automorphism group is that has like G invariant everything, that you're not really improving much. But for these kind of cases, it's very helpful. And another very strong theorem that helps to check K stability or k-poly stability is the Avant-Zhuang theorem. And this theorem is very helpful to bound local delta invariants. So if we have P in X, a point, this is like a simplified version of this theorem. We take E, a prime divisor over X, such that P is in the center of E, and then let's phi to be a birational morphism. Associated to E. Then we have that the local delta invariant in P is bigger or equal to the minimum of the log discrepancy over the S that we already computed, or the infimum of all the closed subsets which is like, it's basically, so this part is a refinement of a linear series. And here we have the differential. So basically what this theorem says is that we can take what the one of the elements, we can take one of the exceptional devices that we have here, we compute this, and this is going to be bigger than this, or another delta invariant that we are computing in a lower dimension. So the problem gets kind of smaller, like and easier with time. So this is like the three strong results that we use in all our papers so far. So now let's focus on the results. So about the local stability threshold. Any questions so far? I don't know if I think you already saw most of this, but I assume not. So we'll start with the local stability threshold. This has been a study topic because of this reason, no? Like we can use local stability threshold to reduce our problem. And also, since we are reducing dimensions, so if we are, this is the idea of using flags. So if we have an object X, which is the three-dimensional, we can reduce our delta by taking a surface inside here and studying the delta invariant of this D surface, and then we can take a curve in this surface and study the delta invariant of this curve with respect to this previous surface, and then we can take a point in this curve and we can study the delta invariant of this point. So the idea is basically reducing dimensions, getting these some specific formulas for all these things. So we take our big three-dimensional thing and we can reduce it to a surface case and so on and so forth. So it's interesting to know all these local delta invariants for surface cases, so we can after use it to bound the three-dimensional case. So this is more or less the idea. So a lot of people has been working on studying these local delta invariants, and actually these results for both the smooth and singular cases. So the goal, these results for smooth cases, by Araujo et al. In the Calabi book, in the book of Calabi problem for Farnham threefolds. By Yaban Xuan. Okay. Sorry. And by myself on this, and singular cases, Elena Denisova did huge progress on this when studying all these stability thresholds. So we will focus obviously in what I did, but I recommend you to check the other ones too if you are interested. And the case that I studied was the local delta invariant on Del Pezzo surfaces of degree 2. Surface of degree 2. And here, this is an interesting case because this local delta invariant, because we have that this local delta invariant is irrational. And this was at the beginning conjectured to not be possible. They thought all these local delta invariants are always rational. First example was given in the Avang-Xuan paper, where they also give all this idea of flux and valuations. And this is the second example known so far where this happens. And the theorem says as follows, and then we will do a little sketch of the proof too. So let X be in P2 be a smooth Del Pezzo surface of degree 2, and let P0 in X be a point in our Del Pezzo, and we assume there exists a -1 curve passing through P0. Then the local delta invariant in this point will be irrational, and it will be this exact number. The rest of the cases were already studied in the Calabi problem book from Fano threefolds, but this was the only case where they couldn't really compute it. So in the rest of the cases, they compute the exact number. For this case, they had to do a lower bound because they couldn't find this exact number. So I will tell you more or less what is the idea of like how we compute this irrational number. So let me give you some sketch of the proof. So first, we take this point and we do an AB weighted blow up. Sorry if I have some like spelling mistakes. I try to avoid it, but with dyslexia from my papers and my notes to my how I write, sometimes things change. So so we have AB weighted blow up of our point P0 in X, such that 3A is smaller than 4B. Okay, so we have at the beginning our x is the Petzl degree 2. And we have our P0, which is in -1 line. Let's say locally Hubert is 0. And we do a weighted blow up of that point. Let's call this EAB. So now we get to all the special points, and we have a exceptional divisor, which this exceptional divisor, its self-intersection will be -1 over AB. And this L, the strict transform, will be self-intersection minus A plus B over B. So we have this thing. Remember, when we compute this local data invariance, it's important to choose a good exceptional divisor. So in this case, we create one for general AB, and we are going to study this for a general AB. So now we have here, in the moment that we are doing a weighted blow up, we have singularities in our new variety. So the next step is to write the pullback of the anti-canonical divisor in terms of negative curves. In X tilde. And to do this, we need to do the resolution of the singularities on X tilde. Which in this case, because we have a AB weighted blow up, we have two singularities. We have, in one side, we have a 1 over B1 D1 singularity, where D1 is the minus A plus 2B, and Q, which is 1 over A 1 C1 singularity, where C1 is minus B plus A. Okay. So to do that, we find a rational map from Y tilde to the weighted Petzl surface of degree 1. So basically, to have an idea of how this will stay, can I copy here? So here you have, I wanted to, yes, here it is. So you have basically to see the image of how this, because remember that this is any AB. Okay, so you have to do a study of like very general, what happens with what's the relation and all this. It's very similar to having Euclidean algorithm, basically. So you have to like do all these blow-ups until you have a smooth thing. So basically, in general, all this it looks something like this. Okay, so the idea is so we take this, we have our X, we did the weighted blow up. So we have X tilde. And then we solve P singularity. So this will be this side here with the E's to get another thing. And then we solve the Q singularity, and we have a smooth thing. And then we take this and we contract all these -1 curves. You see, like here at the end, the exceptional divisor that we got at the start, which is this one, it will transform until after all these blowups, it becomes a -1 curve. And then we start contracting all these -1 curves until we get a weak del Pezzo surface of degree 1, which is a known algebraic variety. We have a lot of properties. So, and this after we have the relation of, which is what we will get if we, instead of doing a weighted blow up, we get, we do a 1-1 blow up at this point. Let's see. And then here in this weighted, here we are contract all -1 curves until we reach the weak del Pezzo surface of degree 1. And then here we have, so in this case, here we have, basically we have F1, which is a -1 curve. And then we have the transform of L, which will end up being a -2 curve. So here, what we do now is to contract this L, the -2 curve. And then we have a singular del Pezzo surface of degree 1. And in here, we have double cover branching on a sextic curve. Sextic curve to P112. And here we have some good properties. So we basically take the divisors that we have here. So in this case, it will be here and this one that we already have. And we take them back all the way here to rewrite the anticanonical divisor. So here we have the automorphism Y tilde, which is the invariant induced by W, involution induced by W. And then we define this to be V-1 tau V, and this will be in the automorphism of Y, which is an involution in Y. Okay. So after doing all this, now we define D to be the image through this involution. And we check that F1 plus D plus L is -2 times KY. And from here, we going backwards all the way, taking all this way back, taking this and taking all this way back, we manage to get that -2 kx is isomorphic to D, linear equivalent to D plus L. So the way back all the way to here. So we go back, we take this back And we go through all this, and we come back to having an expression for minus 2kx, depending on this new d and l. So all this work is just to be able to rewrite the anti-canonical divisor in terms of negative curves, basically. And we prove that the pullback of the anti-canonical divisor through the weighted blowup is half L tilde plus D tilde plus A plus 2B. So this was the more tedious, let's say tedious part, to get this expression in terms of negative curves. And once you have this, we can do the Zariski decomposition. The third step is then we use Zariski decomposition to compute the volume of the pullback of the anti-canonical minus the exceptional times t, and we get an expression for this, the log discrepancy over the expected vanishing order, which will be 12, 3 plus 2 mu over 15 mu squared plus 34 plus 8, where this mu is the A over B. So then we take this, and what we do is we compute the infimum or the minimum of this function, and we get, taking its minimum, we get that lambda is, the minimum is 1 over 71, 11 plus 8 times square root of 3. And this gives an upper bound for the local delta invariant of this point. And then the last step is to use the Avanchois theorem method to prove that it's also a lower bound. Okay, and to do this, so when we do the Avanchois theorem, remember that we compare what we already have. So this that we already computed. We already compute this. So what we need to study is points in this exceptional divisor. We have to take into account that this exceptional divisor has all smooth points, but 2 singular points. So really, we just need to check 3 cases. So what if a point in this exceptional is smooth and the 2 singular points, and both are bigger than what we already computed? So Avanchois method said that this local delta invariant has to be bigger than this delta. And this will be how we compute this. In some cases, this is like, if you go to the result, which they study cubic surfaces, they already have all the -1 curve, like they already have all the negative curves to describe the anti-canonical divisor, so they don't have to go through all the issues. For the Petzl surfaces of degree 1, I don't think it's done yet, or at least I didn't saw any papers. So I think it will be slightly more complicated than this, because you cannot, some of the tricks we use here, we cannot use it in the Petzl surface of degree 1. And any questions so far with this? I guess all good then. Okay, perfect. So now we focus in another interesting part of K-stability, and which is, I think, the most active right now, which is the study of the Calabi problem for Fano threefolds. So our last point today is the Calabi problem for Fano threefolds. And so what is this? What is the Calabi problem? So the goal is to find all k-polystable Fano threefolds in each deformation family. Uy. Ay. I don't know how to get rid of this. Oh no. Here, okay. Fine. So this was a big progress. We know that we have 100, which are 105 in total. So the steps are the following. First, we need to know which families contain some. Contain k-polystable smooth members. And this was already done by Araujo et al. In 2030 in the Calabi problem book. And so they found 78 families that has k-polystable members. Others do not have even semi-stable. Okay, so there's 78 that have k-polystable members, and the rest do not have even semi-stability. And this is because of openness of semi-stability property. So once we had this in 2023, they wanted to prove that all or almost all the members, smooth members in each 78 are k-polystable. And this is huge progress. Almost there's some families left yet, but I think only some hard ones are left, I guess. And then the last step was to, in each of these families, the 78 families, we want to compactify the k-moduli. So we have the smooth members before, and now we want to compactify it by adding the singular members that are lacking here to get the compactification. So for 24 of these 78, they are zero-dimensional moduli, which means that we have a k-polystable point, but the rest are only strictly semi-stable. So we only have a unique k-polystable element. And then for 6 of them, we have that it's one dimension. So today I will focus in one of this. The example that I did before, so in our paper, we said these 3, 6 one-dimensional ones, that the moduli is in all cases a P1. And we will see more or less what's the method that we use in most of the cases, which is the same system. Obviously, when this dimension increases, we have to do case-by-case study. The methods can be different. In a lot of cases, instead of like studying each individual case, what they have to do is a comparison with like the GIT moduli, for example, and see if there is a relation, if it's the same, if it's the GIT moduli blowing up something. And so you have to study the geometry of each of these families and all these things. So yeah, this is still a big work in progress. So there's still a lot of people working on this. So in our case, which is the one-dimensional one, the idea is as follows. For each of these families. So for each of these families, first, we write the explicit parameterization. The parameterization for smooth members. Which usually is like some A1 minus some points. So we'll have some points missing. And then the idea is to take those points and fill the gaps. With k-polystable singular Banach threefolds that admit a smoothing question. So basically we construct a dominant map. Then after we construct a dominant map, from P2, from P to 1 to each element of the family. So this is the idea in each of these cases. There is some exception, but in general, this is the idea. But as I said, in the moment that you are taking higher dimensions, like for example, we currently have another project with 18 dimension, with the moduli being 9-dimensional. And obviously this method does not work anymore because you don't have points missing anymore. It will be curves, surfaces, like could be something way bigger. So this is a case specific when we have dimension. So now we will go back to our example that I mentioned at the beginning. So we have this. Give me a second. So we have So we have a P. So we have the blow up of P3 in a line and a twisted cubic. So this was the example that we started with. And this can also be seen as 1-3 curves in P1 cross P1. So if we consider just a twisted cubic, and then we embed it in P1 cross P2, and then we blow up its image. Okay, so it could be seen as a blow up of a line and a twisted cubic in P3, or we take a 1-3 curve in P1 cross P1, we embed this in P1 cross P2, and we blow this up to get the same objects, different description. So this was already parameterized by Denisova. Was given by Denisova. And we know that, so for each of this, let me give I think I have here the specific parameterization. Okay, yes. So we have this C lambda curves. So you have U x squared x plus lambda y equal V y squared y plus lambda x. So this is in P1 cross P1. And then we take this and we embed it in P1 cross P2 by taking UV x squared xy y squared. So our elements will be x lambda, the blow up of this C lambda, of the image of this C lambda in P1 cross P2. And these are the smooth members. Obviously, there is like relations between them. Not each of these are different of each other. There is some isomorphisms here. And so we have this. And now for these elements, x lambda, we know that most of them are k-polystable. So if lambda is different to plus minus 3, plus minus 1, or infinity, then x lambda is k-polystable. If x is plus minus 3, then it's strictly k-semistable and degenerates to x0. So it's in the same class afterwards. And if x is plus minus 1, it admits an isotrivial degeneration to x infinity. So what we need to check is that if x infinity is k-polystable. Because if x is k-polystable, then x plus minus 1 is strictly K semi-stable, because we cannot have two K polystable elements that they degenerate to each other. So the next step is, okay, we have all these K polystable ones. X plus minus 3 is strictly semi-stable, but degenerates to x0, so it will be in the same class after the taking all the relations. And x plus minus 1 it has a degeneration to x infinity. So we will need to check if this is K polystable. So then what's the how we describe this? So the first thing we check is that x infinity is isomorphic to taking to the one of the degenerations that I mentioned, which is we have a line separate, and then we were using the description of line and twisted cubic, we degenerate to the twisted cubic to 3 lines, L2, L3, L1. So this will be x1 equals 0, x2 equals 0. L3 will be x2 equal x3 and x1 equals 0. And L1 will be x1 equal x0, x2 equals 0. This is in P3. Okay. Using x0, x1, x2. Okay. And this will be x0 equals 0 and x3 equals 0. Okay. So you have this, I don't want to get into all the details of how you check that this is isomorphic, but it's all in our paper if you're interested. Or if you want to ask later, ask questions. So basically we have this, and we need to check our x infinity is isomorphic to blowing up. We blow up these 3 lines. And we get this isomorphism. Now, what happens when we blow up all these 3 things? We get 2 singularities for these intersections here. So instead of checking the K-poly stability of X, what we do is small resolutions, and we check the K-poly stability of small resolutions. Because we don't want to, dealing with singularities can be a little bit tricky. So instead, what we do is, okay, we have P3, we did the blow up, so we got X, and
can I ask?
yeah.
So when you blow up, does it matter to have different ordering?
Yes, it does. So if we do all together, then we get, well, it doesn't matter or the order of L and the other 3, because they are disjoint, so nothing happens. But when we blow up all together, we get singularities. And now what we are gonna do is the small resolution is, instead of blowing up all together, we are gonna blow up first some, and after the ones that they are disjoint. So what we can do, for example, if we blow up L1 and L3 first, and so we will blow up these 2 which are disjoint, we get something else, and then we blow up the strict transforms of L and L2. And then here what we get is a small resolution of X, which is smooth. But we could choose to do the other way around. We could choose to blow up L and L2 first. Then we will get something else, and we could, after blow up the other two, the strict transforms of the other two. So here we will have another smooth variety, which is different. So there will be some curves that they are switched. But what we have between this is an Atiyah flip. Flip. So these are smaller. So basically, it doesn't matter where you do the computations. You could do it here or here. In this case, it doesn't change. We are just changing some curves. So, and both of them are, these are both small resolutions. So the log discrepancy does not change. And the S invariant or the expected vanishing order do not change. So it is enough to check the K-poly stability to check K-poly stability of this either or tilde. Okay. In some cases, we choose one or the other because remember we are in Fano threefolds, and to do these computations, we need to use a Zariski decomposition. And because we are in dimension 3, Zariski decomposition does not always exist. So we need to choose the model where the Zariski decomposition for the devices we have exists. So sometimes we, even in the same family, we need to be changing models from one to another depending on the computations. And here we do use the theorem of the automorphism group because we have to simplify computations. We use the automorphism group of X. Okay, in this case, we have G, where we can change, if we change X0, the variables to X3, X2, X1, X0. And so we have an involution, and we have R star, C star action. We have X0, X1, X2, X3. This becomes lambda X0, lambda X1, X2, X3 for side of C star. So if we have this is a reductive subgroup of the automorphism group, and that leaves invariant L and L2 are invariant, and L1 and L3 are exchange. So we use this to only having to study, instead of having to check all the exceptional divisors over X, we can reduce our studies to only checking the invariant sub varieties. So in this case, we check the exceptional that comes from blowing up L. So the exceptional that comes from blowing up L2. And then we have this smooth quartic that is x0, x2 equal x1, x3. Smooth quartic. And so these are the surfaces we need to check. And also we have to check, because of course, as I mentioned, we have to check, we are in a three-dimensional thing, so we'll have to check the G-invariant surfaces, G-invariant curves, G-invariant points over this. So the invariant lines are x0 equal ax1 and x3 equal ax2. So here, these lines are in R, and if we take 0, we have L, and if we take L infinity, we have L2. Okay, so this inside of this smooth quartic, we have L and L2. And also we have ax0, x2, bx1, x2, bx0, x2 plus x1, x3 equals 0, where A, B, C are inside of P2. And AB plus C squared is equal to 0. Oh, and it's not equal, sorry. This is different. Yeah. And we take, yeah, so we also study Q, taking this ABC 1, 1, 2. So we focus, instead of having to check everything, we focus in few. There are still quite a few cases, but like as a list, things get slightly easier, and there's no G-invariant points or no G-invariant planes. Points or invariant planes. So this is more or less the idea, I think. So we check the G-invariant things, and then we use the Avanchuan method also to reduce computations and get like lower bounds for all these things. But yeah, if you want more details, you are more than welcome to check our paper where we also defined this function. I think I'm gonna leave it here, so to give you some time for questions if you have any, and yeah.
Thank you very much for the talk. Are there any questions?
So in my analysis, Bong-Jean-Pei, something is the equation for the Kerr-Einstein. So in analysis, we have a stability. Of course, in linearization and the second derivative, we have a stability in the analytic sense. Are they the same?
Sorry, I think I didn't really understand what's the question.
So your K stability is the same as analytic one or not?
Yes, it's analytic, yeah.
Could you give us the obvious reason why?
So the question is, why is the K stability an analytic property? Just to, yes.
That's right.
Yeah, but I think it's a very long story, and that's probably out of the scope of the talk, I guess.
Sorry, I don't understand what the audio is not very good.
Yeah, I think probably it's a very long story. So
yes,
yeah.
The proof of how to analytically, because the analytic definition of K stability was done by Donaldson. It's very, very long. So they use the all these Futaki invariants and all these things to define, like give the first analytic proof from K-stability. So nowadays it's not, we use characterizations mainly, but I think the original papers were from Donaldson or Tian, where they do an analytic proof using Futaki invariants.
Yeah, so here you basically describe the situation where the moduli is one-dimensional. So I'm wondering that in case where the moduli is two-dimensional or three-dimensional, do you have any proposal?
So it's very case specific. So most of the papers, what they do is they compare with some known G-invariant GIT moduli, and they prove that they are the same. Because it's true that if something is K polystable, then it's GIT stable. So they use zero relate, and in some cases it's if and only if. So the idea usually is you try to compare it with some GIT or try to describe it as a GIT moduli and the blow up of this GIT moduli. But it's very, very case specific. That's why it's for all these 78 families, like the progress is very slow.
Okay, yeah, thank you.
Are there any other questions? So for the 6 families in the one-dimensional cases, so you can do it basically the same way, like you have the parametrization?
So all but one, like there was one that they gave us more problems, and we had to use the GIT, so it ended up being the blow up of a GIT moduli. So from 5 of them are similar ideas and similar proofs, but there was one that the K polystable element, it was neither of the ones that you will go through at the beginning. So, yeah.
I see, yeah. Thank you. Other questions or comments? Okay, if not, then let's thank Eroche again.
Thank you very much for having me.
Yeah, thank you very much for the nice talk. Yeah, and I'm sorry for